The basic concepts and underlying issues. Multi-objective problems, MOPs. MOPs comprise several objectives, 2 or more, which need to be minimized or maximized depending on the problem. A general definition of an MOP is: an MOP minimizes fx equals f1x. Fkx, subject to gx less than or equal to 0, I equals 1, m, x ohm. The solution of the MOP minimizes the components of a vector fx, where x is an n-dimensional decision variable vector, x equals x1, xn, from some universe ohm. And MOP includes indecision variables, m constraints, and k objectives. The MOP's evaluation function f, ohm maps decision variable vectors, x equals x1, xn, to vectors, y equals a1, ak. Multi-objective optimization techniques are divided into 3 classes. A priori approach decision-making and then a search. In this class, the objective preferences or weights are set by the decision maker prior to the search process. An example of this is aggregation-based approaches such as the weighted sum approach. A posteriori approach is search and then decision making. The search is conducted to find solutions for the objective functions. Following this, a decision process selects the most appropriate solutions, often involving a trade-off. Multi-objective evolutionary optimization, MOEA, techniques, whether non-Pareto based or Pareto based, are examples of this class. Interactive or progressive approach search and decision making simultaneously. In this class, the preferences of the decision makers are made and adjusted during the search process. Pareto dominance. The idea behind the dominance concept is to generate a preference between MOP solutions since there is no information regarding objective preference provided by the decision maker. This preference is used to compare the dominance between any 2 solutions. A more formal definition of Pareto dominance, for minimization case, is as follows. A vector u equals u1, uk, is said to dominate another vector v equals v1, vk, denoted by uv, according to k objectives if and only if u is partially less than v, that is, i1, k, ui less than or equal to vi i1, k uim, as the problem with n less than or equal to m is irrelevant. Fifth, all the allocated processors will be waiting according to the order of allocation, i.e., after the previously allocated task has been finished the present task can be started. From the literature, it was observed that number dominant properties on WTV problem has been discovered and depicted by the researchers. To start, first for any scheduling sequence R, CT VOF res equal to WT VOF R, where R is the antithetical schedule of R. Second, the scheduling sequence that minimizes WT vis antithetical to the scheduling sequence that minimizes CTV. Third, CT remains unchanged when reversing the order of the last N1 tasks. Fourth, for CT minimization problems, an optimal scheduling sequence is of the form of n-2, n-1, i.e., the largest task is arranged at the first position, the second longest task is arranged at the last position, and the third longest task is arranged at the second position. Fifth, the optimal sequence for a WTV minimization problem is V-shaped. Sixth, PMCT problem is MP complete in the strong sense when M is arbitrary. Seventh, PMTV problem is MP complete in the ordinary sense when M is fixed. Minimization of WTV as a performance measure for task scheduling problem has been discussed in Section 7 for achieving the service stability between the tasks in single processor. The parallel processor is nothing but multiple numbers of single processors with same speed or multiple numbers of single processors with different speed are working simultaneously for achieving the concurrency. Hence, to come up with an optimized schedule, which minimize the WTV is the aspiration of the task scheduling problem in parallel environment. The WTV developed, S.1, in Section 7 will be utilized for the development of the WTV on parallel processors. The WTV of tasks in a complete sequence for the parallel processor is obtained as follows in P.1. The objective is to find an optimum or near optimum schedule with pseudo-polynomial time of qm vertical bar prec vertical bar WT problem by minimizing the variance of waiting time for number of tasks on n number of uniform parallel processors by P.2. Subject to where niche large number Each task is assigned to a position is exactly once in any one of the processor sequence is described in P.3. Each position of any one process or sequence is used exactly once by a task is described in P.4. The waiting time for first task of the individual processor sequence is described in P.5. The waiting time of all other allotted tasks for the individual processor except first one is described in P.6. Eeks. P.7, and P.8, state that if two tasks are on the same processor, then one must be scheduled after the other, otherwise, the values of WK on WTK plus 1I will not be related. Eeks. P.9, and P.10, indicate that the introduced decision variables are binary in nature. Eeks. P.11, and P.12, represent that the value of completion time and waiting time must be greater than 0. The uniform parallel processors are identified by their different speeds. The processors are arranged in chronological order, such that the first processor is the slowest processor with low processing cost and the last processor is the fastest processor with high processing cost. The scheduling problem, QM vertical bar prec vertical bar WTV, discussed above is a combinatorial problem. Therefore, usage of a heuristic is inevitable to obtain solution in polynomial time. The challenge is to distribute the tasks in an efficient manner among the processors. A unique task allocation method named as POOM is presented in Ref. For the allocation of tasks among the processors. Uniform parallel processors consist of a bank of single processors with different speed, and the computational cost is depending on the speed of the processors. It is most important to allocate the task in such a way that the computational cost must be maintained. Hence, the unique task allocation scheme named as POOM is combined with the heuristic methods namely Versus, BS, and RSS is also discussed in Ref. The efficiency of the three heuristic methods with the unique task allocation scheme for uniform parallel processors is tested with a large number of test cases discussed in the next section. To find the effectiveness of these heuristic methods, test cases are randomly generated with the help of 4 probability distributions. At first with the help of normal distribution, 901 numbers of test cases are generated randomly in combination of 5 and 6 numbers of uniform parallel processors for each case of 100 through 1000 numbers of tasks. The test cases are followed by the same number of tasks and processors with the help of Poisson distribution, exponential distribution, and uniform distribution. The performance analysis of the heuristic methods with unique task allocation scheme is discussed below. For analysis, mean WTV is taken as the measure of performance. Performance of measure of 3 heuristic methods named as Versus, BS, and RSS is analyzed by using a unique task allocation scheme named as POOM. This enhances the performance of heuristic methods for parallel processing in uniform processors. The allocation scheme in combination with heuristic algorithms is tested with a large number of test cases starting from 100 to 1000 tasks separately. The results analysis for normal distribution on uniform parallel processor is presented in Figure 5, which consists of 2 subfigures, A, and, B. The mean WTV obtained by the 3 heuristic algorithms with the help of unique task allocation scheme is shown in each subfigure. The task allocation schemes are implemented on each test case generated by normal distributions. The subfigures, A, and, B, represent mean WTV performance for 5 and 6 numbers of uniform parallel processors, respectively. The 3 heuristic methods are represented in each subfigure, A, and, B, by 3 distinct colors. Green color represents Versus method, black color represents BS method, and red color represents RSS method. An enlarged view of mean WTV performance of heuristic methods from total task numbers 221 to 226 is presented in each subfigure. The computational result shows that the mean WTV obtained by RSS methods in combination of POOM is apparently same in comparison with other 2 heuristic methods. Comparison of mean WTV with respect to heuristics methods by using POOM allocation scheme for the processing time generated by normal distribution. Similarly, the processing time for all the test cases is generated with the help of Poisson, exponential, and uniform distribution, respectively. It is also observed that mean WTV obtained by RSS methods in combination of POOM are apparently same in comparison with other two heuristic methods as presented in Ref. Developing an efficient task allocation scheme and execute it with the heuristic methods for uniform parallel processors is NP hard. To overcome it in uniform parallel processor, an efficient task allocation scheme is required along with the heuristic methods. The average time required for finding sequence by computing the heuristics in uniform parallel processor is represented as computational cost. From the above discussed heuristic methods with POOM allocation scheme, it is found that the versus method requires at least 4 tasks to commence, and all the heuristic methods discussed in section 6 need a sorting procedure after the POOM allocation process is over and before the starting of heuristic process.